Welcome to Linear Algebra. We are on the path to linear algebra vitality. Let's follow the path. To begin our understanding of linear algebra, we must discover the meaning of the vector. A vector is an arrow. Have I perplexed you? Did you expect something more complex? Let's translate this into more mathematical terms. An arrow has a magnitude. The magnitude is just the size of the arrow, and the size in this case is the length. An arrow also has a direction. In this case, it is directed to the right. This arrow is a vector. The vector has a magnitude of 3 feet. The vector has a direction of going to the right. The arrow, which is our vector, represents a vector quantity. A vector quantity has magnitude and direction. Remember, the vector is our model of what a vector quantity is, but technically the vector is a model of the quantity, not the actual quantity. A scalar quantity is the type of quantity we are used to working with. They only have a magnitude. Some examples would be having 3 apples, being 5 feet tall, or drinking 5 bottles of water. There is a magnitude, but there is no direction being computed. An easy way to remember this is that scalar quantities can be properly measured with a scale or a similar measuring tool like a ruler. Notice that scalar sounds like scale. Note that a scale does not measure direction. This means a quantity with direction would be a vector quantity, and should be represented by the arrow. An interesting property for vectors is that as arrows, they can represent vector quantities of various dimensions. Here is a vector representing a vector quantity that is one-dimensional. We can see that we move 3 positive units. The vector represents what our vector quantity is, perfectly. Here is another vector that represents a one-dimensional vector quantity. Notice that the arrow moves -2 units to the left. Also notice that the vector makes it clear what the magnitude is, in this case too. It also makes the direction for the first dimension clear as well. You can only move left or right in the first dimension. The negative value indicates left in this case. Here is a vector that represents a 2-dimensional vector quantity. The vector clearly describes the vector quantity. The vector goes 2 positive units in the first dimension. Note that we are using the x-axis as the first dimension in this example. This means the magnitude is 2 units. It also means that it goes to the right on the x-axis. The vector goes 0 units in the second dimension. Note that we are using the y-axis as the first dimension in this example. The vector goes 0 units in the second dimension. Note that we are using the y-axis as the second dimension in this example. This means the magnitude is 0 units. A magnitude of 0 implies that the direction would be staying still, in rigorous mathematical speak. This vector shows us how far the vector quantity goes in each dimension, and the direction it goes in each dimension, making it an awesome 2-dimensional vector. We can make vectors in more and more dimensions, but you get the idea. Here is an example of another 2-dimensional vector. We say that a one-dimensional vector is an element of the one-dimensional real coordinate space. This is represented by an R with a vertical bar to its left. The one-dimensional real coordinate space represents all possible ordered lists of real numbers, where the list is a size of 1. We say that a 2-dimensional vector is an element of the 2-dimensional real coordinate space. This is represented by an R with a vertical bar to its left, to the power of 2. The 2-dimensional real coordinate space represents all possible ordered lists of real numbers, where the list is a size of 2. We say that a three-dimensional vector is an element of the three-dimensional real coordinate space. This is represented by an r with a vertical bar to its left, to the power of 3. The three-dimensional real coordinate space represents all possible ordered lists of real numbers, where the list is a size of 3.